Okay, today's video marks the beginning of Unit 2 in our course, Linear Equations, which involves a great deal of graphing. We create our graphs on what's known as the Cartesian plane, which is just a fancy phrase or name for a grid pattern using x and y values. The x values deal with everything horizontal, and the y values deal with everything vertical. For those of you that are historically inclined, the Cartesian plane was first introduced by a gentleman by the name of René Descartes and has very, very many applications in maths, sciences, navigation, and even the arts. The Cartesian plane is made up of two axes, the x-axis and the y-axis. The x-axis helps us keep track of everything moving horizontally in our world, and the y-axis handles everything moving vertically. The origin refers to the point in the middle of the graph where the x and the y-axes intersect. All right, let's move horizontally to the right 8 units, and then up vertically 6 units. At this point, no pun intended, we'll place a little red dot which we'll refer to as a coordinate. These two values, 8 and 6, help us measure the exact position of this coordinate. The values are always referred to in this order, the x value or coordinate first, followed by the y coordinate, separated by a comma. They are often enclosed in brackets and are referred to as an ordered pair. In these examples, I've plotted a number of points. Now I want to label the coordinates for the point R. So for this one, I'm going to move along 1 unit, and then I'll stop. This point R is not up or down, so there is no movement along the y-axis. So I'll refer to this by the ordered pair 1, 0. For point K, I move along 5 units along the x-axis, and then up 4 units for the y-axis. So I'll refer to this point as 5, 4. For the point P, I move along 3 units along the x-axis, and then I move down 3 units along the y-axis. And because I'm moving down, I'll refer to this coordinate as 3, negative 3. The y value becomes a negative value because it's moving down. For the Q coordinate, I'm not moving anywhere along the x-axis. So that stays at 0, and then I move down 5 units, so this coordinate becomes 0, negative 5. For the M coordinate, now for the first time we're moving to the left along the x-axis. Because of this, we're going to refer to this as negative 6. So 6 units to the left, 4 units down, and again, because we're moving down along the y-axis, this will become a negative number. So our ordered pair is negative 6, negative 4. And for our last coordinate, H, we move along the x-axis to the left 6 units, and then up 7 units. So the coordinate becomes negative 6, 7. We can refer to our movement along the x-axis as the run, and we can refer to the movement along the y-axis as the rise. If we draw a line connecting the beginning of the run to the end of the rise, we get something that looks like a hill, which we will refer to as the slope. In mathematics, we use the letter m as a variable to represent slope. And we can express the value of slope as its rise divided by its run. Imagine you are out walking and you come to a hill that has a fairly gentle slope. The top of the hill is, let's say, 20 meters higher than the bottom of it, and you get to walk 50 paces from the beginning of the hill to the time you reach the top. It's a nice, comfortable climb, not too strenuous. Now imagine you come to another hill. This hill is also 20 meters in height, but it is much steeper. You get from the bottom of the hill to the top in only 10 paces. We've shortened the run, but kept the rise the same, and this has the effect of making the slope much steeper. In this example, we have another slope. Here the run is 16 units across, and the rise is 3 units. Now watch what happens to the steepness of the slope as we maintain the same rise, but shorten the run. The run is becoming shorter and shorter. The rise is still the same, but because the run is shorter, the slope is becoming much, much steeper. Now, let's look at the same kind of slope to begin with, but this time, instead of varying the run, we're going to keep the run constant, but we're going to increase the rise. So the run is still 16 units across, but now as we increase the rise from 3 units to 4 units, watch the slope become steadily greater. Now let's look at some examples that involve numeric values for our rise and run. In this example, we have a run of 3 units, followed by a rise of 2 units. Given that the slope is measured as rise over run, we can say that the slope of this particular graph is 2/3. Now let's consider what that means, a slope of 2/3. What it means is that for every 3 units that we move along the x-axis, we are moving, in this case, up 2 units along the y-axis. In this example, we move along the x-axis 3 units and then go up the y-axis 3 units as well. Our slope can be expressed as rise over a run, or in this case 3/3, which is further reduced to 1. This means that for every 1 unit on the graph that the graph moves horizontally, it moves 1 unit vertically up the y-axis. In this example, our run is 5 units along the x-axis and then down 5 units on the y-axis. Because we are going down the y-axis, we refer to it as a rise of -5. So now our slope is -5 over 5, which reduces to -1. This means that for every unit we move across the x-axis, we move down 1 unit along the y-axis. And if you run a line from the beginning point to the end point, you'll see something that we'll refer to as a negative slope, which is why it's expressed as -1.